Hi, and welcome to this section of the Physics 3 tutor. And in this section, we're going to continue talking about capacitors. Here we're going to talk about what capacitors look like when we actually put them in an electric circuit. So that's really what capacitors are used for. They're in almost every electronic device you can think of. Your computer chips, your computers, your phones, everything has capacitors in it, and it's really, really useful. They serve many purposes. But the central reason that we use capacitors in circuits is because they store electric charge, and we talked about that in the last section. So here we're going to talk about when we put them in a circuit. So we're going to start drawing some circuits from here in the next few sections, some basic circuits to kind of understand how electricity is going to flow. And we've talked a little bit about that already, and we'll look at, in specific, we'll look at putting these capacitors in series and in parallel arrangements. And that's sort of a fundamental thing. We'll talk about it here for capacitors. We'll talk about it later when we talk about resistors. And it's sort of a fundamental electrical thing. So let's talk about that now. So a capacitor is what we talked about in the last section. It's usually two plates of material, two plates of metal, separated by, could be air, could be just an air gap, it could have some other material in between there. We'll talk about what that is later, some plastic or some non-conducting material between the plates. The plates never touch. They're very close together. So you can think of two sheets of paper very close together. And of course we have our little terminals coming off that we connect to the rest of the circuit with. And so usually the capacitors that you see in your computer or whatever, they're cylindrical, and that's because they're literally rolled up like you could think of paper towels if you want to think of it that way. A really thin material wrapped up on itself. Of course there's a insulating material between the plates so they never touch, but they're really tightly wrapped, and that's why they a lot of times look cylindrical like that. The other thing I want to say, and we talked a little bit about this last time, the unit of capacitance is a farad. A farad is a huge value of capacitance. So you'll never see a capacitor in your computer or anything have a 1 farad value. You'll always see them really measured in microfarads, so 10 to the minus 6 farads, or even picofarads, nanofarads, especially when you start looking at the capacitors on a, like on a computer chip. Those are incredibly small values of capacitance. So don't think that you're going to start dealing in farads. If you calculate an answer to one of your problems that is, in terms of farads, 5 farad capacitor, probably made a mistake somewhere, or the problem wasn't really realistic. Okay, so there's two main ways that we're going to talk about capacitors in this section: in series and in parallel. And we'll talk about it also for resistors. In series, you can think of the capacitors lined up end to end, really. So we'll draw a picture in a second, but you can think of a capacitor here and then another one right here, and they're connected, and you just literally lay them end to end in the circuit. And in parallel is sort of the opposite of that. It's when you would have a capacitor and then one sort of right next to it. So let's start talking about capacitors in parallel circuits. All right, in parallel circuits. And so the basic thing to think about here is a very simple thing. And keep this in your mind also as we go through the course, because when we get to inductors and resistors and other circuits later on, we'll have the similar arrangement for different components. So here's a battery. Remember, a battery almost looks like a capacitor, except it has a longer line and then a shorter line. The longer line is telling you which terminal is positive on the battery, and the shorter one is telling you which terminal is negative. So you don't really have to write positive and negative. If you draw a symbol like this, you know from looking at it that the longer line is always positive. So you can think of positive current flowing this way. And in real life, the electrons are really the things that are moving. So the electrons are going this way. But when we talk about electric circuits in physics, and also when you get into electrical engineering, even though the electrons are the things that are actually moving through the circuit, we generally don't talk about electrons moving, because electrons are negative, and then all of your currents would be negative, and you would have lots of negative signs going everywhere for no reason. So having a negative current going this way is exactly the same thing as having a positive current going the other direction, algebraically. So we always talk about positive current. So even though all of you know electricity is really electrons, when you're talking about circuits, we don't talk about electron motion. We talk about these positive, they're called holes, because the electrons have sort of left behind a hole there as they move along. So we think about a sort of a fictitious positive current going this way. The algebra gives the exact same answer as if we had just chosen and looked at the negative current going the other way, and we have a lot cleaner math because of it, because of those negative guys that are gone. So here is one capacitor. If we were going to put a capacitor here, we have two plates that would have the same length. And this guy is just one battery and one capacitor. So I'm going to label this guy C sub 1. And so when we have, in a simple circuit like this, you know, you could have a switch here if you wanted and shut the switch. Then the current is going, the electric current is going to flow this way. It's going to begin to pile up on this plate of the capacitor. So what you're going to end up having is a positive Q sub 1 pile up on there. I'm labeling it 1 because this is capacitor number 1. And then on the other side of the plate, you're going to have an equal mirror charge, negative Q sub 1, that's going to basically appear there. And so at the end of the day, this should make a little bit of sense to you. I have a positive terminal here, so I should have a positive charge buildup on this plate of the capacitor. I have a negative terminal of the battery here, so I should have a negative sort of charge buildup there. And they're equal and opposite in magnitude just because of the fact that it's the only thing connected there. So when we say a capacitor has charge Q, what we really are saying is that on this plate we have positive Q, and on this plate we have negative Q. So together we say, okay, this capacitor has charge Q. Now I'm not going to draw it here because it'll get cumbersome, but inside the plates of the capacitor, we really have an electric field. I'll draw it here to the side just to show you. But between the plates we have a little electric field because electric field always goes from positive charges and they end up and terminate on negative charges. Remember back from earlier in the Physics 3 series. So inside of every capacitor is an electric field. And that electric field, we're going to learn later, is along with the charge that's present, is really what's storing the energy inside of the capacitor, because electric field can store energy. It has the capability to do work. Electric field can move charges around. So when we make this arrangement like this, the larger the plates in this capacitor, the higher the capacitance we have, then the more electric field that we have in there, and the more charge that we have built up there. So we have more energy stored in that capacitor. One more thing I'll say, and we'll keep going in a second. When we have this positive charge pile up here and this electric field kind of spring up here, then what it's basically doing is this electric field is, these positive charges are here and this electric field is here. The negative charges arise, obviously because we're connected to a battery here, but also when you have an electric field pointed that way, then all of the negative charges that would happen to be in this wire right here, they're going to be attracted because the electric field is pointing this way. Remember, in an electric field, the positive charges go with the field lines and the negative charges go against the field lines. So any electrons here in this plate or near this plate are going to be attracted to the plate. The negative charges will, because of this electric field that's in the middle. And also, the positive charges will be on the other side of the plate for the same reason, because the field is going this way. So you can sort of think of these charges on this other plate as induced charges. Charges that, if you want to think about it, the current piles up here, and then this sets up an electric field, which then pulls electrons over to the other plate. So they're sort of induced. The reason I'm telling you that isn't because you have to think about that in your circuits. You don't have to think about that in your circuits. But in a second, when I do a proof and show you something, we're going to revisit that in a second. So let's put this on hold here. I think it's fairly self-explanatory. You have positive charges piling up here and negative ones piling up there, and you have some energy storage in that capacitor, and everything's wonderful. So let's go on to adding another leg here. So let's say we have another battery, totally separate circuit. This voltage, I'm going to put this V here. This voltage is also V, so it's the same battery. Could be a 9-volt battery, could be something else. Here's my capacitor, same exact thing as before. I just don't want to clutter up this drawing. So I have C sub 1, and what I'm going to have here is I'm going to go and add another capacitor, and I'm going to add this one. We're going to say this is in parallel. And so when you see two capacitors where they're lined up like this is what's called in parallel. So that's what we're studying in this section. So this could be capacitor C sub 2. And on this capacitor right here, we're saying the same thing as before. This has some Q1 on this plate, and this has some negative Q1 on this plate, and this guy has some Q sub 2, and this has some negative Q sub 2. So it's the same value of the charge, it's just opposite on the other side of the plate. And notice that because these are in parallel, what it really means is they're both connected directly to the battery. That's one thing you have to look at when you're thinking about circuits and just really start to understand it. It only comes with practice. Is you have to think about this a little bit. Pretend this capacitor isn't even here at all. This capacitor really is connected directly to the battery because these are wires that go all the way to the other capacitor. So it's almost like, from this point of view, this capacitor really isn't even here. This guy is connected directly to the voltage source, which is right here. And this capacitor here, yeah, this guy's in the circuit too, but he is also directly connected to the voltage source. So really, you know, it's obvious in this guy. If you were to put a voltmeter, you know, a little meter that you can buy at Radio Shack or someplace else, and if you were connected across there, then you would read, you know, you would read the voltage V. So if this were 9 volts, you would read 9 volts when you connect it across. Because even though the capacitor's here, you're connecting your meter directly to the battery terminal, so that's what you're going to measure. The same thing is actually true here. So if I connect a meter here, you know, and I connect it here, I'm going to measure the same voltage V. So if this is, you know, a 10-volt battery, then I'm going to measure 10 volts if I put a voltmeter right here and try to measure it. If I put my voltmeter here, I'm still going to measure 10 volts. If I put my voltmeter here, I'm going to measure 10 volts. Because no matter where I am in the circuit, I'm measuring the potential difference between the battery terminals. Now, if there's another capacitor here, or a resistor, or some other electronic component, then that's not true. In other words, you might measure a different voltage. But here, I'm basically connected directly to the battery. So let me draw one more. And I think you get the point, but I really want to make sure nobody's lost. So this will be plus and minus. Let me draw C sub 1 again. And we'll draw C sub 2 again. Right? So the same as that capacitor. And we'll draw a third capacitor, C sub 3. Right? And just to keep everybody happy, I'm going to go ahead and label the same thing. So Q1, negative Q1, Q2, negative Q2, and this will be Q3, negative Q3, right? So there's different charges that are piling up on the different capacitors depending on the value of the capacitor. And the same thing holds true here. If I take a voltmeter and I hook it up between these two terminals right here, I'm going to measure the same voltage V, because even though all these capacitors are in the way, my voltmeter is really connected directly to the battery. So what I'm trying to say is, and I'll write some of this down in a second, is that when you have capacitors in parallel, every one of those capacitors sees the same voltage as the source that you've connected to, because they're all in parallel. They all see the same voltage. So it's something you need to remember. When you have things in parallel, they all see the same voltage. That's going to be a huge helpful trick for you when you're solving your circuits, to know that when you look at that, it's the same voltage. Because you'll see the equations of circuits aren't that complicated, but you do need to have some intuition to know what's going to happen. That's one of those things I'm trying to teach you here. When you have things in parallel, the voltage is basically the same. Now, when you put them in series, which we're going to look at in a second, that's not true. The voltage is not the same across things that are in series. We'll talk about why here in a little bit. But for here, just sort of memorize that. So the voltage is different. I'm sorry, the voltage is the same. Let me write some of this down. So I'm going to put the voltage is the same across the capacitors. Same voltage. All right, so that's sort of like thing number one to remember. Thing number two to remember, the charges that are stored in those capacitors are different. Are different across the various capacitors. You may not realize that at first, but the reason that they're different is because, remember the equation of capacitance, or the equation that relates capacitance. For capacitor number one, I can say the charge stored on this capacitor is equal to capacitor number one times the voltage. Remember, Q is equal to CV. Q is equal to CV. You should remember that. Now, for this guy, let me switch colors here. The charge stored on capacitor number 2 is equal to C sub 2 times V. Notice it's the same V in each case. The voltage is the same because I just told you the voltage is the same no matter what capacitor you're looking at. And then over here for number 3, Q sub 3 is equal to C sub 3 times the voltage. So basically, if you put a 9-volt source here, then there's going to be a 9 volts here, a 9 volts here, and 9 volts here. Okay, but each of these capacitors can be different. This could be, 1 microfarad. This could be 5 microfarads. This could be 10 microfarads. So they're all going to have different values of capacitance. When you do these multiplications, you'll get different amounts of charges stored on those capacitors. So when they're in parallel, the capacitors can have different charges stored on them, which is what I have written down here. The voltage is the same across all of the capacitors when they're in parallel. So that's an important thing to remember, and it's gonna be helpful for you. Now, if you think about it, here's the circuit in parallel. This battery, the same voltage is everywhere. You should think about voltage or electric potential, if you want to think of it in terms of electric potential, which is the same thing we talked about in the last volume of Physics 3. Voltage is sort of like it's almost like pressure in a water hose. You know, we have this idea that voltage really. Let's see, I'm getting a little bit ahead of myself, but in the movies you'll hear people, they were killed by 100,000 volts of electricity. Well, volts really doesn't have anything to do with how much electricity is flowing through your body. Voltage is analogous to, in a water hose, it's how much pressure is pushing the hose out. Now, how much water actually comes out of the hose is basically going to be equivalent to the electric current. When the current flows through your body, that's what stops your heart. The electrons moving through your heart, damaging the muscles and everything, that's the actual thing that kills you. The voltage is simply the electromotive force, is something a lot of your books will have, but it's the sort of the force, for lack of a better word, that is then allowing the electrons to move by pushing them, so to speak, which is really the electric field doing the pushing, and it's pushing the electrons out. So when you have this voltage source here, it's pushing electrons out. Well, since they're in parallel, this battery can deliver a different amount of current to this leg, and a different amount of charge to this leg to be stored, and a different amount of current to this charge to be stored. And that's because they're in parallel. So you can have the current going here, branching off, delivering 5 coulombs of charge here. It could continue on and deliver 4 coulombs here, and it can go over here and deliver 6 coulombs to be stored in this capacitor. That only works because they're in parallel, because of the way things are arranged. The current can split off and do this. I'm sort of telling you 3 or 4 different ways the same thing, which is the voltage is the same, the charge stored on these capacitors can be different. So what we want to do next is we want to figure out, all right, let's go to the lab and build a circuit. I'm going to put so many capacitors in parallel like this. How would I calculate an equivalent capacitance? In other words, if I have 3 of them in parallel, how could I calculate what an equivalent capacitor would be that would be exactly equivalent to the 3 of them I just put in parallel? It turns out you can do that. And you can do it later on when we talk about resistors and other electronic components. You can simplify the circuit quite a bit by looking at it that way. So what we want to do, let's say this is 1 microfarad, and this is 2 microfarads, and this is 3 microfarads. Is there a way to calculate what an equivalent single capacitor would be that would represent the 3 that are here? And that's what we're trying to do. So let's go and do that now, and we'll do it right over on this board right here. So we want to find an equivalent capacitor. So we want to find an equivalent capacitor for the parallel, and you need to get used to me writing this. This is parallel, the parallel arrangement. So anytime you see this, it means parallel. So that's what we're talking about here. How do we do that? Now, I can just tell you the answer. I can just tell you the answer. I'll tell you right now. All you do is you add the values of these capacitors up. So you add 1 microfarad plus 2 microfarads plus 3 microfarads, and that would be the same thing as an equivalent capacitor. In other words, what we're trying to do is we have maybe we have 15,000 capacitors, and they're all in parallel. What we want to do is figure out what single capacitor, C equivalent, could I go buy from the store that would be exactly equivalent to, however many I had put in parallel. How do I do that? How do I calculate that? And I told you the answer. You just, if they're in parallel like this for capacitors, you add them up. But why does that work? And by the way, when we get to series arrangement later, it's not going to be that simple. You don't just add them up. So you might think, oh, this is really simple. You just add them up. But you have to do some thinking as to why that's the case. So I think that since this is a physics course, instead of just a straight circuits course, I'll take the time to show you why that's the case. So let's do that real quick. It's a really simple proof. So we want to find an equivalent capacitor. So what we need to do is remember that when we have these guys in parallel, the total charge stored by this arrangement here, see, this stores charge Q1, this stores charge Q2, and this one stores charge Q3. So the total charge stored by this entire bank of capacitors is equal to the sum of all of those charges. So, because it's different charges there. So the total charge stored by that arrangement is equal to Q1 plus Q2 plus Q3. The three charges that were stored in the three capacitors. But also remember that this is equal to, because we just wrote this a second ago, C1 times V plus capacitor 2 times the voltage plus capacitor 3 times the voltage. And we wrote this down here just to sort of remind you. The equation that governs capacitance, the charge that's stored is equal to the capacitance times the voltage. Now in parallel, the voltage is all the same, and that's why V is all the same. So this is a nice little equation that we're able to write down. Total charge is summed together is equal to the sum of each of the capacitances multiplied by the voltage. So if we were going to go one step further here, then I would say, all right, so let's do this. We'll say Q total is equal to Q1 plus Q2 plus Q3 is equal to, I can factor out of V because V is voltage and it's the same everywhere, so C1 plus C2 plus C3. I can just basically pull that out. And so remember back that where you're trying to really go with this is, in general, this equivalent capacitance, C equivalent, is going to equal to Q total divided by the voltage that's applied. So you can just think of it this way. You know, I always think of it as Q is equal to CV. Well, that applies to whatever the equivalent capacitor is here, because in this equivalent capacitor circuit, I'm applying some voltage, V, right? And there's some charge, Q total, let's call it, Q total, which is stored there. So you got to think of this as sort of an equivalent arrangement. No, this is not what you built on your lab bench, but it's exactly the same thing, because I'm basically storing so much charge. I've got that represented here. The voltage across these capacitors is the same as this one, and I'm trying to calculate what the equivalent capacitor would be. So the equivalent capacitor is simply going to be the total charge stored by the arrangement divided by the voltage applied across. And I have everything I need to really go and solve that now. So the equivalent capacitor, so EQ I'm going to say, is equal to Q total, and Q total is equal to this stuff here. So the V times C1 plus C2 plus C3. So it's equal to Q total divided by the voltage, the applied voltage. And notice that these voltages cancel out. In other words, it doesn't matter what voltage is applied. It doesn't matter at all which voltage is applied. So the final answer is, for parallel capacitors, then an equivalent capacitor is equal to C1 plus C2 plus C3 plus ... because if you could have 10,000 capacitors, which is equal to, if you wanted to write it in fancy terms, the sum of I is equal to 1 to n of C sub n. So that's another way you might read it in your book. This is just fancy math speak for saying, hey, however many capacitors you have, add them up. So let me go ahead and box that, and we'll talk a little bit more about it. This is basically the result you need to remember. I could have just started this section and not given you all this background. I could have just given you this equation, and I could have said, hey, capacitors, when they're in parallel, you add them together. And then you would have been okay, and you would have gone and you would have been fine, your problems usually. But I don't think you would have understood quite so in detail why that's actually the case. So this is the reason why. Basically, any arrangement of capacitors, the equivalent capacitance is going to be equal to how much charge is stored there divided by the voltage. Now, we could figure out how much charge is stored because of the arrangement. The voltage is in the top and in the bottom, and so it eventually cancels out. And so what this tells you is that when you put capacitors on a breadboard or on a circuit board, then the equivalent capacitance has nothing to do at all with what the voltage is, which totally makes sense. You should be able to just look at the values of the capacitors you have and calculate an equivalent without, irrespective of anything else in the circuit or anything else, as far as a voltage source. It should only matter on what you've actually put on the board as far as the capacitors, and that's what we've learned here. So burn this in your head. Capacitors in parallel, you add them together. Capacitors in parallel, you add them together. Capacitors in parallel, you add them together. All right, so let's go. And what we want to do next is we want to talk a little bit about the series arrangement of capacitors. So we've talked about parallel, you know what that looks like. Let's talk a little bit about what would capacitors look like if you put them in series. So let's look at that here. Capacitors in series. All right. Capacitors in series. So the circuit is basically going to look like this. And I'll draw it a little bit different just to make it a little bit different. So my voltage source, I'm going to put sideways here, but notice I've still got a long bar and a short bar. So this is positive and this is negative. And it's voltage V. Could be 100 volts, could be 10 volt battery, could be whatever. All right, so I'm going to draw a big wide circuit here. And up here, I'm going to have a capacitor. And then I'm going to give me some space, and I'm going to put another capacitor. I'm going to give me some space, and I'm going to put another capacitor. And then I'm going to complete the circuit, right? You always have to complete the circuit. So these are in series. Now, just for comparison's sake, go back and look at what it looks like in parallel. In parallel, you've got your voltage source, but the capacitors are basically bridging across and directly connected to the source like this. Each end of the capacitor effectively is directly connected to the battery terminals. This one's connected directly to the battery terminals. This one's connected directly to the battery terminals. They're all in parallel like that. Over here, that's not the case. This capacitor, for instance, is not directly connected to the battery terminals. Both sides of this capacitor is not directly connected to the battery terminals, and the same thing here. So this one is more like, like what you do in basic, elementary school. You put 3 light bulbs in series, and if this capacitor, explodes because you put too much current in it, no, the circuit is opened, and then the whole circuit doesn't work anymore. So this is what we call in series, when they're basically daisy chain like this. All right, so let's draw a few things. Obviously, I think not a big surprise. Let's call this capacitor C1, we'll call this capacitor C2, and we call this capacitor C3. Now, here, what we need to do is label. What I'm going to do is I'm going to label this one positive Q and negative Q. This one's positive Q and negative Q. And this was positive Q, and this is negative Q. All right, now notice, very important, it's very subtle. I did not say this is Q1, Q2, and Q3. I labeled them all Q. What I'm basically telling you without telling you is that the charge stored on each of these capacitors when they are in series is exactly the same. So see, there's a little duality. When it was in parallel, the voltage was the same across all of the capacitors. When they're in series, the charge stored in all of these capacitors is the same. So it's not quite the same case. That's because they're arranged differently. Now, one more thing let me write that's going to, I think, make it a little bit clearer. If you were to get a voltmeter, you can buy those from the store, and you put it between this capacitor right here, then you would measure, let me draw a little dotted line here. You would measure, that's what these little dotted lines, this is like a measurement. This would measure V sub 1. Now let me finish and I think you'll see where I'm going with this. If I measure between these two guys, then I would measure a different voltage, V sub 2, right? And if I would measure down here at the end, let's call it right here, then if I put my voltmeter here, I would measure yet a third different voltage, V sub 3. So these voltages are totally different. And that's because you can sort of think about this, it's basically because it's arranged differently. This battery is not connected directly to this voltage source. So the voltage that happens to fall across this battery is not going to be the same as this voltage source. This capacitor is not connected directly to this voltage source. Totally anyway, it goes through all these other components. So the voltage here is not going to be exactly the same as it was in the last problem because it's not connected the same way. So one thing that you may not understand at first, but you'll get the hang of as you work circuits is, the total voltage across the whole thing is V, and if you were to measure this one, and then measure this one, and then measure this one, and then add the voltages together, the total voltage as you measure across each component and then you add them together, that must equal the total voltage across the whole circuit. Because this voltage, let's say it's 9 volts, this voltage is 9 volts between here and here, 9 volts across here and here. So that means whatever voltages I measure along the circuit, they must sum up to 9 volts because you've connected the battery across the whole thing. So they must be split in such a way that they all add up to 9. So major difference between series and parallel for capacitors. Let me write some of this stuff down. Okay, when we have here, let me go back and review here. In this case, voltage was the same across the capacitors because of the way it was arranged. Here, let me put a little star here, voltage across the C's, the capacitors, are different. And then I'll put they must sum, I'm going to capitalize it, up to the total voltage that you apply, V. Now, a little aside that I'll say, this thing we're talking about is for capacitors. It totally applies to resistors, it applies to any circuit. If you have something in series like that, the total voltage drop that you measure across each little component, it must add up to the total voltage drop that you have across the whole thing. It's just the way it's done here. The second thing I want to write down, let's go back and review this one. The charge on these capacitors were independent because of the way we connected it. The charge is basically stored differently in each capacitor. You can have a different value of charge. In this arrangement, the charge on each capacitor is the same. So, you might hook this up and find out that there's one microcoulomb charge stored here. And if you could measure the same thing here, it'd be 1 microcoulomb here, and it'd be 1 microcoulomb there. All right? So that's very, very important, and it's going to be directly useful in a lot of your problems, and it's just something that you'll have to kind of get used to. The charge is the same there. Now let me give you one aside and tell you why the charge is probably the same there. And you can think of this current, when you hook this up, the current comes out and starts to pile up on this plate of the capacitor. Now once this happens, there's an electric field that ends up basically pointing this way inside of the plates from positive over here. And so the electrons in this little segment of wire here, they get attracted to this guy here because of the electric field, and so all the electrons begin to pile up here. Now because I have attracted most of these electrons away, then what I'm left with over here is a net positive charge that ends up piling on this plate. So because there's a positive charge piling up on this plate, I have an electric field inside this capacitor going that way. And let me just do this here. So this is the electric field inside there, right? And so because of that, I have exactly the same thing. I have negative charges attracted to this plate, which leave behind positive charges over here, which set up yet another electric field here. And then the same exact thing happens over here. So you see, it's sort of a chain reaction in this case. And here, over in this arrangement, they were independent. The battery could supply different amounts of current to different leg of the circuit, but here, it's not independent. So whatever is delivered to the first capacitor basically is going to ripple through, and I'm going to have an attraction of electrons leaving behind positive charges. Same thing is going to happen. So I have Q1 here stored, and then I have the same charge stored here, and the same charge stored here. But notice for the middle capacitor here, it's storing a charge, but it's getting all of its charges that are piled up on these plates just from the wire that's really surrounding it. It's not even coming directly from the battery. The battery supplies the charge to the first capacitor, but in between here, it's basically sucking up charges from the surrounding little neighborhood and getting there. So yeah, it's storing charge, but it's not really storing charge that's delivered by the battery. So basically your circuit, when you're in series like this, is going to be governed by the first capacitor there. So you can think of it as, just yet another way to talk about this is, here, when we have three capacitors like this, we might have Q is equal to C1 times V, capacitor 1 times the voltage drop across that capacitor. We'll call it V1. And then for the second capacitor, Q is equal to C2 times V2. So the charge stored here, which is labeled the same. Q is the same in both cases. Capacitor 2 times voltage drop across this capacitor. That's the charge stored there. The same exact charge is going to be capacitor 3 times voltage 3, which, remember, voltage 2 and voltage 3 and voltage 1, they're all different. They must add up to equal this voltage here. So in each case, the charge stored on the capacitors is exactly the same. The capacitances are different, but the voltages across each of these capacitors is also different, and that's really what allows that to happen. So, if you were to look at this, you would see, just to kind of solve for a different variable here, V1, the voltage across here, is equal to Q over C1. And this guy, the voltage 2, is equal to Q, which is the same Q stored on it, divided by C2. And here, voltage 3 is equal to Q over C3. So the different voltages can be calculated just like this. So I'm kind of going a little bit in circles, but I'm getting to a point because what we want to do is we want to now calculate what is the equivalent capacitor for this arrangement, for when capacitors are in series. Now you're not going to add them together. I'll just tell you that's not the answer. And let's go ahead and derive what the answer is and see how it differs. What we want to do is we want to calculate an equivalent capacitor, C equivalent. And we know that if we could take this arrangement and replace it with a single capacitor, that single capacitor would have a charge stored on it, and that charge would be charge Q, and it would have a voltage which would be across it, which would be the voltage of the source here. If we replaced everything with a single capacitor, the voltage across it would be V like this. All right? So when we go and do this, the charge Q that's stored on this capacitor is just Q, just like we might think. What would be the voltage? How could we rewrite the voltage? Well, I already told you that this total voltage is basically going to equal to this voltage plus this one plus this one. So I've already written these down here for you. You could probably wonder, why did he do that? Well, that's because I'm going to use it now. So let's go ahead and write this down. So V1 plus V2 plus V3 is going to equal the total voltage. So let's use what we've got here. Q divided by C1 plus Q divided by C2 plus Q divided by C3. All right, and whenever you look at this, you'll realize I could cancel this Q with all of these because I could factor out a Q on the bottom and it would cancel on the top. So the equivalent capacitor in series, the equivalent capacitor is equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus ... You might have 55 capacitors in parallel, but this is a little bit ugly the way it's written, 1 over and then a bunch of other stuff like this. So typically the way you write it and see it written in your book is 1 over the equivalent capacitor, because if I take 1 over this, I can take 1 over this, and then I'm going to move everything in the bottom up. So it's going to be 1 over C1 plus 1 over C2 plus 1 over C3 plus ... which is exactly equal to the sum of I is equal to 1 up to N of 1 over C sub I. 1 over C sub I. So if you had 10 capacitors in series, basically what it's telling you is you do exactly the same thing. 1 over C1, 1 over C2, 1 over C3, 1 over C4, 1 over C5. You add all that stuff up, and that answer that you get is not equal to the equivalent capacitor. That's equal to 1 over that. So you have to invert the thing again. And we'll do that when we do our problem. So this is what you need to remember. Really and truly, it's this one, this bottom one, that's the one that you need to remember. So I could have, and this is the main result that I want you to remember, if I could have just started off and said, okay, hey, there's 2 ways to put capacitors in a circuit. One of them is in parallel. And when you do that, here's what you have to remember. The equivalent capacitor of any arrangement of capacitors in parallel is just add the capacitances together. Boom, you get another capacitor. Okay, cool. You can go buy that third one from Radio Shack and build your circuit. Now when you have them, I could have told you, in series, all you have to do is you have to do a little bit more math. 1 over the first capacitor plus 1 over the second plus 1 over the third, on and on and on. You add all that stuff up, and then you have to invert it again, 1 over again, to basically solve for your equivalent capacitor, and then you have it that way. So I could have just told you that, but I wanted to give you a little bit more, I guess I should say, mature understanding of it, just because. This is the most important thing to understand for the section, obviously, and for those of you going into electrical engineering, you don't have to keep track of what charges are, I mean, you don't usually have to deal with that when you're solving a circuit. There are certain things that you do when you're solving a circuit. One of the most important ones is figuring out what the equivalent capacitance is. But in physics, it's important to know where these things come from and to know that the charge is the same when they're in series. And the charges are indifferent when they're in parallel, because on your physics test, you're likely to be asked things like that. So I wanted to go and tell you that stuff and show you how it's proven. All right, but certainly these are the most important things to remember. So what we're going to do is erase the board and work some problems and begin to get a good understanding for how to use these things. It's one thing to learn about it, it's another thing to work some problems and say, okay, now I know how to do that. It's not going to be that big of a deal. You'll find out. The math is not crazy hard, but I do think it's important for you to kind of know you know, enough about how these things are derived to be able to say that you truly understand it. So let's go ahead and erase the board and start working some problems. Okay, now we're going to begin working our problems, and you're going to find that everything we learn is really important to know to enrich your understanding of what's happening, but really when you start to work some of these problems involving circuits, mostly what you're going to be tasked with is understanding series and parallel and sort of how to calculate equivalent capacitance and what that sort of means. If you can master that, you'll do fine in your problems. First problem is, how many 1 microfarad capacitors need to be placed in parallel in order to store a charge of 1 coulomb with a potential of 110 volts across the capacitors. So how many 1 microfarad capacitors need to be placed in parallel to store a charge of 1 coulomb with a potential difference of 110 volts across these capacitors? Ultra important. Always write a drawing. Draw a drawing. It's going to help you. Because if you just stare at this, you're not going to really know what to do. So it's telling you that you have 110 volts. So let's draw that, 110 volts. And so that's going to be like this. And I'm going to have this guy here. This is plus and minus, right? 110 volts. And it tells me how many of these 1 microfarad capacitors. So let me go ahead and put one here, one capacitor here. Let me go ahead and stick another one here. But ultimately, I don't really know how many I have. So I'm just going to kind of remind myself of that. I'm going to kind of draw a third one here in a dotted fashion. You know, then I could have another one even out there. So I'm not going to continue that one. And each of these capacitors is 1 microfarad. And this is the same thing, 1 microfarad. So I'll do it and draw it like this. 1 microfarad. All right, so the question is, so now when you look at a drawing, you're thinking, oh, I can totally get it. It says how many 1 microfarad capacitors can be put in parallel, so you have to make sure and draw them in parallel, each of them 1 microfarad, in order to store a charge of 1 coulomb. In order to store a charge of 1 coulomb when I have this guy here. So the thing when you have something like this is to realize that you're basically going to need to find an equivalent circuit. So because these guys are in parallel, the equivalent circuit is equal to C1 plus C2 plus C3 plus dot, dot, dot. Now, I don't know how many capacitors I need. In fact, that's the whole point. So I could have N capacitors. I don't really know. But I can tell you that if I have N capacitors, it's going to be N times 1 microfarad. That's going to be the total equivalent capacitance. If I have N capacitors, it's just going to be how many capacitors I have, if they're all the same value, times N, because I'm just adding them all together. So that's going to be the same thing as something like this, 1 times 10 to the minus 6, because that's a microfarad, right? So that's how many I have here. Now the second part that you really need to pay attention to and to realize is that for capacitors, the charge stored in a capacitor is always equal to the capacitance that you have. In this case, it's an equivalent capacitor representing my circuit times the voltage across that capacitor. Now, if I have, let's say 8 capacitors in parallel, what I'm saying is I can replace it with a single capacitor. That single capacitor will still be connected directly to 110 volts. So the voltage across it is the same as the voltage across all these guys. If I put it in there, it's going to be 110 volts. So what I'm going to do is just kind of make this substitution. So the problem says I want to store 1 coulomb of charge. So that goes into here, 1 coulomb of charge. And then the equivalent capacitance that I have is just N times 1 times 10 to the minus 6, right? And then the voltage that I have is given by 110 volts. So now I have everything in place to solve for N, which is the number of capacitors that I need, right? If you take 1 and divide by this and then divide by this, you're going to get 9,090 capacitors. All right, it's a great example of a problem where you have to understand the idea about series and parallel and how to calculate an equivalent capacitor, but you do have to use your brain a little bit because you need to get an expression for the equivalent capacitor in terms of N, in terms of the number of capacitors, and then realize that since you're trying to store a certain charge in this equivalent capacitor, you can set it up like this, where this is the equivalent capacitance, this is the voltage across, and then you solve for the number of capacitors that you're going to need, which is what the problem actually was asking about. All right. The next problem says what we're going to do is we're going to find the equivalent capacitance of this circuit, and so I'm going to draw the circuit now. let's say you just have an arrangement of capacitors. And so this is a capacitor here. This is another, let me make it a little bit more manageable. This is another capacitor here, right? Now that's a little bit too easy. Let's add another one like this. A third capacitor out like this. So there's 3 capacitors. This one over here is 4 microfarad. This one over here is 10 microfarad. And this one over here is 5 microfarad. Notice they're all microfarads, like I told you. You're never going to have farad capacitors. All right, now you can think of your eyeball sitting here looking in. If I put let's just pretend that I had a capacitance meter. And I put this capacitance meter here. What I'm basically asking is, what would that meter read? Because that's going to be the equivalent capacitance of this entire arrangement. Notice I've got 2 capacitors in series, and then this whole thing is in parallel with another capacitor. So you have to use your brain a little bit here. And basically what it's saying is, if I put a meter there, a capacitor meter, then I'll read the equivalent capacitance of this arrangement. Same way of saying, okay, now I want to go to electronics store and purchase a single capacitor that would be the same value as what I have here. So pretend your eyeball here looking in, what's that equivalent capacitance going to be? What's that equivalent capacitance going to be? You need to do one thing at a time with circuits. Okay, this is fairly simple really, but you need to make sure and do one thing at a time. So what we're going to do is do what we know how to do first. Obviously, I've never taught you how to simplify an arrangement with 2 in series and 1 in parallel, but I have taught you how to calculate the capacitance of 2 capacitors that are in series like this. So let's work on only that first. How do we do that? So if we had 2 capacitors here, and that's all we had, and the first one was 10 microfarads, and the second one was 5 microfarads, and I could ask you, how do you calculate the equivalent capacitance? And you would be like, oh, I know how to do that. We already learned how to do that. So that's what we're going to do first. All right, for series arrangement of capacitors, 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2. So 1 over the equivalent capacitor is equal to 1 over 10 microfarads. 10 times 10 to the minus 6. Never forget, don't work with 10 here. You got to have the micro. You got to do your metric system right. So this is microfarad, so 10 to the minus 6 has to be in there. Plus 1 over 5 microfarads. So 5 times 10 to the minus 6. So in your calculator, literally, you're going to have 1 divided by 10 times 10 to the minus 6. That's going to give you a number for this. You're going to do something similar for this. You'll add them together, and then you'll keep going. So 1 over the equivalent capacitor is going to be equal to this. When you divide this in your calculator, you're going to get 1 times 10 to the positive 5. And this, when you do this division in your calculator, you're going to get 2 times 10 to the 5. Right? So then you can add those numbers together. So you'll have 1 over equivalent capacitor is going to be equal to 3 times 10 to the 5. Now, when you get to this stage, you're thinking, what do I do? Well, it's basically, simple algebra. You multiply by this and divide by this. That's one way to think of it. But since this is 1 over C equivalent, if I invert this side, then I must also invert this side. So what I end up doing is 1 divided by 3 times 10 to the 5. So if I take in my calculator 1 divided by 3 times 10 to the 5, I'm going to get 3.33 times 10 to the minus 6, and that's in farads, which is the same thing as 3.33 microfarads. That's the equivalent capacitor. So what we have found is that when we take these 2 capacitors and put them in series, then just these 2 guys together yield an equivalent capacitance of 3.33 times, or 3.33 microfarads. 3.33 microfarads. So that just equates to this. So what we have done at this point, really, is let's redraw our circuit just to kind of make it totally clear. So we've sort of simplified it now, where this first set of capacitors here is equivalent to 3.33 microfarads, right? That's these guys in series. We made an equivalent there, but we haven't done anything at all with the 4 microfarads that are over there. Okay, so this is 4 microfarads. So now we've sort of making one step at a time progress. And so these guys are in parallel now. Now, what do you do with 2 capacitors that are in parallel? Well, you just add them together. So now, working with this circuit, the equivalent capacitor is equal to 3.33 microfarads plus 4 microfarads. And when you do that, it's the same thing as, just to make it totally clear, it's 3.33 times 10 to the minus 6 plus 4 times 10 to the minus 6. So the equivalent capacitance that you have is 7.33 times 10 to the minus 6, which is the same thing as 7.33 microfarads. 7.33 microfarads. So if you were literally building a circuit and you wanted to know what the equivalent capacitor of this was, what this is really telling you is, instead of going to the store and buying 3 separate capacitors and then wiring them up like this, it is exactly the same as just going to the store and getting this value capacitor. Electrically, it's the same. So, I mean, obviously it's not wired up the same way, but looking from the outside in, looking from these terminals in, if I take this and instead of all of this junk and I just put one single capacitor with this value down here, you're basically going to have the circuit behave in the same way electrically. So, we've had a good introduction to circuits and capacitors. I do want to work some more problems of this type, and we're going to do that in the next section. We'll have a few more, a little bit longer, a little bit different. Let's go ahead and work those now. It's important to understand this stuff. You will be asked it on your test. You will be asked to probably prove a little bit of the things that we've talked about here, and you'll certainly be asked in order to be able to figure out the equivalent capacitor of something. So let's go ahead and go to the next section, and let's work some different types of problems, but really involving capacitors and circuits.